I've started looking at the exams, but I never have a good assessment when I start looking. So what's going to happen is I'm going to get through the grading. It might be tomorrow that I get through all of it. Sometime by next week, I'll be addressing the exams. So what's going to happen is I'm going to show you the distribution of scores, so you'll know where you're at, and then I'll discuss that in the context of grading. What I'm kind of looking for is clustering effects, so groupings. So if you're right next to somebody that has some score, I'm not going to draw a line right through you guys, and say, well, that's my arbitrary threshold. So I'm going to see how people kind of group together. Most people in this class should do pretty well. That's at least my expectations. My prior is that you're graduate students and you guys should be able to get pretty good grades. Sorry if I made it a little bit long, but hopefully it reinforced some concepts and you went home and you studied and all of that. That's kind of at least what the real point is. So it's not equivalent points per se. So more on that next week. The final exam, some of you have inquired about that, so what I thought would be fair, or at least reasonable and respectful of your time at the end of the semester, our exam is scheduled for the 15th, and I wanted to give you a take-home and give you a little bit of time to digest the questions and think about them and be able to write things out. I don't want to give you a computational exercise. I might give you some extra credit computational stuff if you want more practice at it. But about 10 questions or so. I want you to think about things and maybe provoke you to think about things that we haven't exactly covered in class and really detail what some of the points are of what we're doing. I imagine it'll take you about 10 hours or something like that is kind of my expectation. So I always estimate high. I'd like you to think about it for like 50 hours, but you might be able to get through it fast and still do well. So I'm not sure. My expectations are usually a little bit misaligned with yours. So I'm thinking what I could do is get it to you on the 12th, and then say by the 15th, by 5 p.m., you turn it in to me then. So it'll give you at least a lot of time to think about it, and you're not under a ton of pressure. Does that sound reasonable? Okay. So if you have any questions or comments or suggestions, we're kind of under new modalities nowadays, with technology and everything that's going on. So if you have any ideas, let me know. I try to do things in your favor. Okay. So I'll say something about that on Slack soon if somebody doesn't quack at me. Okay. I was going over the homework from last time with Echo, and it seems like nobody knew how to do this problem. There were a couple of you that did, and I was impressed. So you figured it out. There was a hint in one of the review sessions that I wrote an identity down, and it was necessary to do this problem. The identity looks like this. So this is called the Sherman-Morrison. I think 1S, I could be wrong, Woodbury formula. And this is 4 determinants. And there's a couple different versions that you'll see. Usually when I used to hear about Sherman-Morrison-Woodbury, there was a version for inverting matrices. So inverting small blocks of the matrices, matrix, so you don't have to do the full matrix inversion all at once. And it shows you how to compartmentalize it into small blocks. So there's other forms of this. This is the result that you get when you apply a determinant to their formula. So that's kind of cool. And it looks like this. It says if you have some determinant, and I'll write this down, A plus, and there's some generalities to this. So it could look like this. This is going to be a vector right here. These can be matrices as well, but we're going to apply it in vector format. I'm going to write this down, x transpose, right here. So this is going to be a vector. And this is going to be a vector right here. So this is going to look like this direction, and this one's going to go in that direction, right there. So this is an outer product. This is going to form a matrix. This is a conformable matrix to that. So this will be a matrix. And this will be a matrix. And everything is conformable so that I can do this multiplication. You can add dimensionality to this if you'd like. But this has to be a valid multiplication. And this needs to be the same dimension of this after I do all the multiplication. So this whole thing is going to be a matrix. This can be rewritten like this. And this is the part that's important. There's going to be a few pieces right here. So there's going to be a term here and a term here that I'll write down in a second. But basically, you can do something magical with this, where I can throw B inverse right here, A inverse right here, and what you end up doing is you have to transpose all of that. And you're going to have some things that don't matter in your problem that show up as proportionality constants, and this is going to be A and B. So this is kind of like factorizing out the matrix. And you can play around with this, and you can apply this formula and use this formula. And how you would prove this formula, you should probably do it for like a 2x2 and then apply induction to it. What I usually do is I go to a matrix algebra cookbook for like derivatives and whatever and identities, and I look up these forms when I see things. This would have been ambitious for you. This is the first time, and it could be because I inserted it into the review. In 15 years that I've taught this class, I always throw this problem on there that nobody came and said, how do you do this? I'm stuck. We'll see how to apply this in a second. So it appears in this problem. So remember I gave you this prior to play around with. This is going to be a normal likelihood right here. So this thing right here, the likelihood for sigma, it looks like this. X and mu. This is going to be proportional to sigma to the minus 1/2, e to the minus 1/2, xi minus mu, sigma inverse xi minus mu. So just the normal thing that we normally play around with. And then I product this up. So these are all multivariate normal realizations. That's the likelihood for a multivariate normal. You're going to apply the flat prior to mu and upgrade that to a random variable as well in this so that you can come up with that. So you're going to take this likelihood function. I guess we can think about it as a function of both sigma and mu. Write down that likelihood. We're going to multiply by that prior. We're going to also use this prior. So if I multiply all these things together and throw that into the integrand, then our job, if we want the posterior distribution on the margin of mu, we have to integrate over a matrix. I would probably write it like this and throw that -1 right inside of there so that I see the terms show up the same. I gave you the prior on sigma, not on sigma inverse. So this is not a Wishart. This is an Inverse-Wishart. So it's being applied in the inverse direction. And so to do this integral, the way I've been teaching you how to do things is to look for the normalizing constant. So you're going to look at the, depending on if you're going to work with sigma or sigma inverse, that'll determine whether or not you use the Wishart or the Inverse-Wishart. Now, some people, I've seen this before, they say, I don't know anything about that other version of the Wishart, so I'm just going to transform that. Remember, when you take derivatives over functions like this, you probably are going to need to look up how you take that derivative. You can think about it a lot, because they probably don't teach it to you in calculus class. But in your matrix cookbooks, there will be some identities for you to apply. And it shows up as this big tensor product thing, and I've worked it out before.
What would you transform it to?
The inverse. So you'd invert it. And you can see what that prior is. This prior is special. This is the Jeffreys prior for this problem. So So I'm not going to have you work that out. But if you wanted to invert it and put it on the other scale so that you can use the other form of the Wishart, you'd have to do some math. My recommendation is just use it the way that it's set up. Go to your distributional handbook and look for the normalizing constant to the Wishart that we're using right here. In this case, it's going to be the Inverse-Wishart. So, and it's a different normalizing constant. Anyway, when you do all that, you're going to work out the normalizing constant that you're going to get for this problem is going to be this. I won't do it. Most of you got right here. So sum of the xi's minus mu, xi's minus mu transpose minus n over 2. So that's what you end up coming up with at the end of the day. So this thing is going to be proportional to that. This is the normalizing constant that you're looking for. So in terms of my notation on the board, this has something to do with that determinant of omega. That's the normalizing constant that shows up. And you're supposed to convince yourself that this is a multivariate T, but it does not look like a multivariate T right here. So multivariate T's look like this. And this is going to have some number of degrees of freedom. So I'll write down nu. It's going to have a centering matrix, or a centering vector. So let's just call this maybe n. So this is going to be a vector. And this is going to be a scale matrix. I'm going to call it sigma. And so this thing looks like this. So I'll say the random variable here is z. So let me just write z is distributed. That's just a dummy argument. So multivariate T's are like multivariate normals, but they have this degree of freedom thing. It lifts the tails up, which is different than variance. So it changes the tail dynamic. It's very useful. I'm going to have you play around with this a little bit more in the next homework. I didn't give you that homework this weekend because I want you to enjoy Halloween. So go enjoy the holiday and I'll have something for you on Monday. This looks like this. 1 plus z minus m. So these are the same dimensions. Transpose sigma inverse z minus m. And then this is going to be divided by the degrees of freedom. So I'll write that down as nu. And this is going to be raised to the minus nu plus, and I have to say what dimension this is. So I'm going to say z is 1 by k. Let's say it's k by 1. It's a vector like that. So the dimensionality shows up right here, k divided by 2. So remember in the scalar form of the T distribution, that's a 1 right there because it's a 1-dimensional vector. So this is the multivariate T. And this hardly looks like this. So they're both scalars. And that's what PDFs are. You plug something high-dimensional in and you get a number out. So this is a scalar. It's a determinant, but it certainly doesn't look like that at first glance. We apply this formula. So let me just show you how to do that before I tell you about detailed balance. We'll come back around to detailed balance in a second. This is the formula that we use to prove that Metropolis-Hastings works. So I'm just going to do the same thing that we did last time. When we did all of this, I know where this thing is centered. Where's it centered? Not mu, because mu is the random variable in this context. So we've switched the roles of these.
Z?
It's not z, so this thing right here. There's no z in that equation. So you're right. This right here is centered at m.
So x bar?
Is x bar. So for the exact same reasons that when you square something, it's centered at x bar. And we proved that. in the one-dimensional case. This is the exact same thing. So this is kind of like what squaring might look like in higher dimensional form. So this is the outer product though. So it's going to be centered at x bar for the same reasons. And so we're just going to play around with this and use that. So I goes from 1 to n. This is a sum. This is going to look like xi minus x bar plus x bar minus mu. And I could switch the direction of these, and maybe I should have done that. But I'll just leave it like this. xi minus x bar plus x bar minus mu. Transpose. Close the determinant. We'll do the same thing that we did last time. And I'll expand this out into its 4 terms. It won't surprise you that the cross term is going to cancel. It's going to be 0. I'm going to have something like sum of the xi's minus x bar and sum over that, and that's going to be 0. So I'm not going to write that down. This will just look like this. Sum I goes from 1 to n. This will be the xi minus x bar, xi minus x bar transpose, plus there'll be a 0 in there. That's the cross term. I'll just add it for notation. And then you're going to have this other cross term, this one with that. X bar minus mu, x bar minus mu transpose, and the determinant, raise it to the power. So same exact thing. So now I'm going to slide my summation operator through. This will look like this. Sum I goes from 1 to n, xi minus x bar, xi minus x bar, transpose, plus this thing is a constant with respect to the index. There's no xi's right here. So this is n times this thing, this outer product. So same thing. Everything right? Cool. Now we can apply all this in a second. Anybody recognize this? Certainly like the nugget of the thing that we use to estimate covariances usually.
Sum of variances.
Yeah, exactly. I think I know what you just said. So usually we end up estimating, I'll call this thing S, is going to be sum of the xi's minus x bar xi minus x bar transpose over n minus k. So again, k is the dimensionality of the problem. So this is the unbiased estimator for sigma, for the covariance estimator. This is what most people will use. So let me just write down the expectation of S is equal to the covariance matrix. If you divide by something different, I don't actually care. So n should be moderately large anyway. So I usually use biased form, but that's just my preference. Does it really make a difference? If it did, we've got bigger problems. We need more data. So, but some people like the unbiased condition. Okay, so this looks like n minus k times s. I'll just give you some notation. So I'll just redefine that. So I have this matrix, this outer product right here. And what I want to do is I want to apply this formula right here. And so in our case, this almost looks the same. I've got this vector right here, and I'm outer producting it, and that shows up right here. And I don't seem to have anything right in the middle, right in there. I'll write it out like this. There's nothing in the middle. Oh, I made a mistake. And we knew this. So this gets switched. Why didn't you say something? I know you knew. So how do I know? Okay, you know Sarah. Yui's going to come up to me at the end of the lecture and say you made a mistake. The reason I knew is Yui got this right. So, good job. Did you have to look this up, or did you get it from my review? Or did you know it?
I looked up. Yeah. I thought I needed something to convert a matrix to a scalar, so that's right.
That's a skill. So that is an absolute skill to be able to go do the research and find the identity. We used to have to go to the library to do this. It's crazy. Nowadays it's all out there. But good job, that is the skill. So terrific research skill at work. So you flip this thing around and it becomes an inner product. So sorry about that. So this looks really similar. In our case, we're just going to let that be the matrix 1. Not the identity, just the scalar. So there's a 1 sitting right in here. So I'm going to apply that. I'm going to throw this thing over here, and I'm going to take that 1 and I'm going to invert it over here. Keep in mind what just happens when I have this number 1 that's inverted. This whole thing is now a scalar. So I'll write it down with the determinant and make that point in a second. So we're going to apply this formula. I'm going to get rid of it for a second and just apply this thing. So let me just write down, this is S n minus k plus x minus x bar. I'll spin these around if you don't mind. X bar times 1 mu minus x bar. And there's an n in here that we have. This is transposed minus n over 2. So here's the magic. I'm going to keep the determinant symbol. This is going to come over here, 1 inverse, that's still 1, plus mu minus x bar, transpose, S times n minus k, invert, mu minus x bar, close determinant minus n over 2. Determinant of the scalar is that scalar. So this is a scalar, you can tell right here. If everything, all the dimensions match, this all works out. So I'm going to just get rid of that.
So what did you do with the n?
Say what? Oh, and I forgot my n. Yeah, thank you. I'll throw it right there. So I'll chisel away at this a little bit more. I'm going to get rid of that minus sign, plug it right there, and take my n minus k and divide that right there. Getting rid of the determinant, this is just a scalar. So I'm going to take this n, and I'm going to throw it here as well, inside of the inverse. So that invert pulls it over here. So now I have things pretty much set up right. What do we do over here? Minus k plus k. Same trick that we did before. Now we're done. So there's your degrees of freedom. It matches right there. So degrees of freedom. Here's your scale matrix. So the unbiased estimator of covariance divided by n. We get more and more precision as the sample size gets bigger and bigger. So we're driving down that covariance structure with n. Where's everything centered? In x bar. That's what t's look like. So there you go. So you can go review this, put it down, and you'll never forget how to do it. So I thought you guys should know, since so many people were almost everybody made it to this. That's your identity. Excellent work to those of you that figured it out. Okay, let's do something new. Let's do detailed balance. I've been telling you about this for a while. So detailed balance is the formula that we use to show that Metropolis algorithms work. When I say Metropolis, I mean Metropolis-Hastings, and I also mean things like Gibbs. Okay. So here's the formula, detailed balance. It looks like this. I'm imagining that this is any old random variable that you want to consider, theta, so it could be matrices, it could be vectors, it could be scalars. So they're transition points, right here. I'll tell you what all these terms are in a second. But if you took everything to be probabilities or probability densities, this formula would make sense to you. This looks like a conditional probability, so conditional on theta, what's the probability that I'll see theta prime? In Markov chains, the context of this is the transition of transitioning from this point to this point. So theta and theta prime are just 2 points in this space that we're sampling from. Let me just say that. Theta prime and theta are 2 points. If they were scalar, they would be points. So usually I use the term realization. So from whatever the sampling distribution is. So realization. In our space. So let me tell you again what our goal is when we apply Metropolis. Our goal is to sample from some distribution. Usually something like this. So in the context of our problem, the way that I'm writing this down more generally, this is the stationary distribution of the Markov chain. So stationary distribution. And so we're going to sample from some distribution. The distribution that we want to sample from is this thing. So in the context of a Bayesian analysis, this is the posterior. Oh, and this is theta prime right here. So this is the posterior. And the whole thing is to prove that the posterior distribution is the thing that satisfies this equation. So again, like in the context of just a exchangeable distribution, something that's conditionally independent, this is what you would think of as the marginal distribution. So that's the margin, and this is the conditional distribution, if these are all going to be equal to each other. So what I'm saying is, this looks like this. Probability of A given B times the probability of B is equal to the probability of B given A, the probability times the probability of A. So same sort of thing that's going on right here. What we want to show is that the posterior solves this equation. So just to be clear about all of this thing right here is the sum over probability of A and B, where I'm summing over omega B, the whole space of B. I'm marginalizing out. Okay, Metropolis-Hastings looks like this. You can't really answer this question of what is this thing without understanding what the algorithm does. So the Metropolis-Hastings algorithm are these 2 steps. So what I'm going to do is I'm going to propose, I'm going to get theta star from some distribution. It's got to be Markovian. Can't be anything that's beyond Markovian. It could be an independent thing. So this is going to be given where I was last time. So this is step 1. And step 2 is my acceptance step. So this is going to be the minimum of 1 pi theta star given x over pi theta t minus 1 given x g theta star given theta t minus 1 g theta t minus 1 given theta star. And then we accept what this probability. I'll just write down theta t, my updated value is going to be either theta star or I'm going to stay at the same location. And this happens with probability alpha. This happens with probability 1 minus alpha. So that's kind of our final step. I always consider this to be part of step 2. So we make that decision. So propose, make a decision. This is how the algorithm works. So this is transitioning you from theta t minus 1 to some new location. Either I stay in the same location or I move. That's what this represents right here in a more abstract, generalized concept of just any old 2 points. So say I'm here, what's the transition rate of moving to some other point in the space? And that's detailed through this algorithm. It tells you how to do it. Here's the process. So the reason I call this a rate and not a probability and not a density is think about these 2 steps right here. If theta was continuous, this would be a continuous thing right here. And then I have a coin flip right here, a discrete move. So both things happen. It's continuous, it's got this density form in the proposal, and then it's got this discrete Bernoulli thing for the second step. We do the same thing if I wanted to know the total rate. I just multiply these 2 things together. So just like if I wanted to know the joint probability of something, I take 2 probabilities and multiply them together. If I wanted to know the joint density of something, I take 2 things and I multiply them together. This is neither a density nor a probability, both in 2 different steps. So our transition, and let me give us just a little bit more notation. I'm going to call this alpha. Let's call this theta star given theta t minus 1. So this is the acceptance probability of moving from theta t minus 1 to theta star, just so I can give us some notation. I would call this theta star given theta. So it would be 1 minus that same thing, not moving to theta star, staying at the same location. So that's what determines the transition rate, is these 2 steps. So the transition rate is the product of these 2 things. So let me just write that down. I just use the term rate, so I can avoid calling this either a density or a probability. It's in the continuous form where theta is continuous. It's got both things going on. So this is going to look like this. Theta prime, given theta, is going to be alpha theta prime, given theta, times g theta prime, given theta. So this is the density in which I propose to move there, theta prime, and this is the acceptance probability. So again, I'm doing both things. Let me just ask you a question, because I've had this question before. Are these 2 things independent of each other? They're obviously not. I propose theta star, and I use the theta star down here, so they're conditionally independent. And I take those conditionally independent things and I product them together. So this is conditional independence, but it looks and feels like independence for a second because I'm just multiplying it together. Okay. Let's put all this together. I'm going to do a typical sort of mathematician thing where I'm going to say I know something. So without loss of generality. I'll tell you why I know this in a second. So I'm going to say pi theta star given theta t minus 1. Let's do this in the same notation that we've had before. Theta prime given theta. These are just 2 points in my space. I'm not going to index it using t for arbitrary reasons. Pi this is not right. Theta prime given x, pi theta given x, divided by g theta prime given theta, g theta given theta prime. So this is the thing that appears over here in the acceptance probability, just with our new notation of these 2 points, theta and theta prime, that I'm considering. I'm going to generalize this over all theta and theta prime in a second. But I'm going to say I know something about this. I'm going to say that this thing is greater than 1. I have 2 points. So let me just write this down a little bit differently. This is exactly the same thing. Theta prime given x, g theta given theta prime is going to be greater or equal to pi theta given x, g theta prime given theta. So it's exactly the same thing. I have 2 points, and I've got these functions that I can evaluate, at least up to proportionality. So I can evaluate this, I can plug everything in right here, and I can evaluate whatever number it is. I can do the same thing right here. I'm just saying I know which one is bigger. So for theta prime or theta, I know which one of those is bigger. One of them is bigger than the other, or they're the same. All I'm saying is I know which one it is. So that's not a very big generalization. So I haven't lost any generality here. And that's what mathematicians mean when they write down W1. So one of them is bigger, I know what it is. This is not meant to be elusive. Okay. So now we just have to play around with our formula real quick. So I'm going to consider moving in these 2 different directions. So I'm going to say, let's consider the transition. I'm going to say theta to theta prime. And I'm going to think about what this transition rate looks like. So rho theta prime given theta, the transition rate is going to be my acceptance probability times my proposal. So this is g theta prime. First I have to propose it to move there, and then I have to accept it. So I have to do those 2 things to get there in this Markovian step. Propose that point, and then accept it. And so this part is easy. This is still just g theta prime given theta. What's this acceptance probability? So remember what it looks like just real quickly. Alpha theta prime given theta is equal to the minimum of 1. Yes. So this is the thing that I have to evaluate. I just said I know which one is bigger than the other. So this thing is greater than 1 right here. So this is bigger than 1. The minimum of some number 1 and something that's bigger than 1 is 1. So that's where my without loss of generality goes. If you didn't want to do that, you have to do the proof in both directions. It's just a waste of time. So times 1. And that's it. So I know what that thing is. Going the other way, transitioning from rho If I started at theta prime, going to theta, this happens in the reverse direction. So what would happen right here, I would have to do these same two steps, and I would have to evaluate this probability right here. So I first have to compose it, G theta given theta prime, and then I'd have to accept it. And that happens with this probability inverted, upside down. So I'd have to accept this thing. So this would be pi theta given x times G theta prime given theta divided by pi theta prime given x G theta given theta prime. And this number is smaller than 1. It's the invert. So again, I'm trying to move from theta prime to theta. So I'm moving from this point right here to that point. And this is the thing that's flipped upside down. And that number is smaller than 1. It's between 0 and 1 because of my without loss of generality. Now we can use these two things and verify that the only function that solves this is the posterior. And that'll tell us that we're sampling from the posterior, that is the limiting distribution. If I keep walking through this Markov chain, I'll eventually be sampling from this thing. There's some probability of being in these states. Probability is not quite the right word if I'm in a continuum, but I'm going to use that word anyway, just because we understand what we mean. So let's do that. Now I just need to verify everything. So I'm going to write down, let's just keep this as a placeholder, what these things are. So this part right here, and we'll leave this just as a second. We'll pretend we don't know what it is. We're not sure maybe which functions go there, but I know this thing right here. This is going to be G theta prime given theta, and I'll multiply by 1 just as a reminder of what we did. And then we have this thing over on the other side. G theta given theta prime, pi theta given x. Theta prime given x. This will be G theta given x, G theta given theta prime, G theta prime given theta. And so our goal at this step of the proof, because we know what the transition rate is, you can think of it as maybe a conditional probability if you'd like, because it is, or a conditional rate, conditional density thing, whatever that thing is. I've got this right here, and I need to know which function satisfies this equation in general. And that will be the stationary distribution of the Markov chain, i.e. what it eventually samples from. And you can verify for a second what it is, what's going on here. We see this over here, so I'm just going to cancel these over the equations right here. How convenient. Those cancel right here. The question is what satisfies this in general? We can see there's only a couple things left. So which function would I need to multiply by for this all to work out? This has to be pi theta given x, and this has to be pi theta prime given x. I.e. that cancels that, and this one cancels that, so 1 is equal to 1. The left-hand side is equal to the right-hand side. There's only one equation, one formula in the world that I can plug in right here if I were to generalize this over all theta and theta prime. So this has to work, it's a function of all across all theta and theta prime. There might be some other numbers that I could throw in here for any particular value of theta and theta prime, but in general, for this to work across all points theta and theta prime, this is the only function. So what that says is pi theta given x, our posterior distribution, but this would work for anything. that I was trying to sample from is the stationary distribution. So a little narration on this. Metropolis had figured this out for symmetric distributions. And 3 years later, Hastings came in and said, I know what rule I need right here so the detailed balance holds. So basically, he said, I want this thing to be the stationary distribution, and he backwards engineered this and figured out what he needed to write down right here for this to be equal, the left and right hand side. That's what I do. So I always am imagining some sort of mechanism for transitioning through the space, and I always try to figure out what my Metropolis decision rule is here so that I'm sampling from the correct thing. The stationary target being the posterior. So when I build MCMC algorithms, new algorithms, I'm doing the same thing Hastings did back in 1957, is just trying to figure out what rule makes this adhere to detailed balance. And I force all my students to do it, and when they don't do it, and they're like, well, I just kind of intuitively thought it's like this. And then we check detailed balance, and it's like, there's your variable. It's in your theory. So this is the master equation for MCMCers. They'll probably apply. There are some new things that people try to do where they want to be more creative in how they bounce around the space, and there's something called leapfrogging. And it turns out it does not adhere to detailed balance. That's another branch of theory. We're not going to cover that in this class. So there is another set of equations that people can apply for some more advanced MCMC techniques, but those are relatively new. So we're going to hold off on those. Anyway, I'll probably ask you in the future to show me maybe what is the reverse transition for a Gibbs algorithm. So you can be thinking about that over the weekend, since I won't give you a homework assignment. Anyway, that's it for now, you guys. Go enjoy Halloween, be safe, and I'll see you guys on Monday.